This video's difficulty is not typical of my target audience, so here is a list of prerequisites before we begin. In my previous video, I covered an overview of what we're doing and a bit of why. You guys gave a lot of great feedback on it, and I felt like I didn't really do a good enough job the first time. So this time, in addition to introducing some more content, I will be revisiting the ideas in the first video in greater detail and hopefully more clarity, with a more structured high-level picture. If you haven't watched the first video, I recommend watching the introduction and first chapter to understand the motivation and what we're trying to accomplish here. Otherwise, we will be diving straight into the meat of the subject, which is the complete algorithmic solution to finding closed forms for all hypergeometric sums and identities. This topic will require another few videos to get through, but starting here is where it gets more serious. Don't hesitate to pause and digest the content as needed. Remember that our goal here is to find a closed form for any hypergeometric summation if it exists, and be able to prove our result. Let's take a minute to review what hypergeometric means. A geometric sequence is when we start with a number and each successive term is multiplied by the same ratio. The geometric series is simply the sum of the terms of the sequence. A hypergeometric sequence is simply a sequence where the ratio between successive terms is not constant, but outputs of a rational function. The hypergeometric series is once again just the sum of the terms of the sequence. So if we have the first term and the rational function, we have the entire sequence. The basic idea for solving hypergeometric identities is going to be this. First, we turn the sum we want to solve into a recurrence, which is a functional equation that might look something like this. From here, we can solve the recurrence and get our closed form. We will look at each of these two steps separately. Another quick note about the terminology. In general, a recurrence refers to a functional equation, but in this video series, all of our recurrences are linear. While we are here, let's also explain what the order of a linear recurrence is. Suppose we have a recurrence that looks like this. We call this a first-order recurrence, because f of n plus 1 appears in the recurrence. A recurrence like this would be second order, since both f of n and f of n plus 2 exist. Basically, the difference between the smallest and largest inputs of the function gives us the order of the recurrence. Before diving straight into hypergeometric sequences and series, let's take a minute to talk about the individual terms. It turns out there is also a general form for hypergeometric terms. To get a feel for what it might look like, let's start with an arbitrary rational function for the ratio of consecutive terms, and multiply the ratios one by one to obtain our terms. Once these ratios are expanded, you can group the factors like this. Notice that each of these groups of factors can then be rewritten in terms of factorials. The constant here tells us which term we have, so making it a variable gives us the general nth term. This isn't the most general form of a hypergeometric term, but hopefully this gives us some insight. Namely that due to the way the rational function ratio works, we get a lot of factorials being multiplied and divided together. With some rearranging and algebraic manipulation, the general form of a hypergeometric term can be expressed like this. We can prove this works by simply taking two adjacent outputs and showing that the ratio between them is always rational. As long as an expression can be written in this form, then it is a hypergeometric term. However, this is simply the one-variable form. There's also a two-variable form that is doubly hypergeometric for both variables, which we will typically denote as n and k here. And multiplying successive terms in either the n direction or the k direction would give us the general term. Once again, here is the general form, and by dividing successive terms, either with successive n's or successive k's, we will get an arbitrary rational expression. So this is a hypergeometric term in general. While it may look really scary, just know that it is merely multiplying through a bunch of mostly factorial terms, with each of them being a linear combination of n, k, and a constant. This general form isn't critical to the understanding of the rest of this video, but I figure that since we are solving all hypergeometric sums and identities, it would help to have a better understanding of what hypergeometric terms look like. For instance, suppose I wanted to find this sum here. Are the terms being summed hypergeometric or not? Would the algorithms mentioned here be able to help us solve it? Knowing that these binomial coefficients can be written in terms of these factorials, we can easily see that all of the factorials are linear combinations of n and k, which means this is hypergeometric. Not every case is going to be as straightforward as these, but it should help you identify many hypergeometric identities more easily. Be careful though, as there are some tricky cases if you aren't paying close enough attention. Consider this example. Notice that 2n choose n is hypergeometric, and so are 3n choose n and 4n choose n. However, the generalization an choose n, where a is an arbitrary parameter, is not hypergeometric. Something that is important to point out though, is that even if the hypergeometric terms are not adjacent to each other in any direction, the ratio between them is still always rational. Imagine I made a table of these hypergeometric terms. We know, by definition, that orthogonally adjacent terms always have a rational function ratio. Since these two terms are adjacent, the ratio between them is rational. Let's call it R0. These two terms are adjacent, so the ratio is also rational. Let's call it R1. We continue in this way, carving a path to the target destination. The ratio between these n terms is simply the product of all these ratios, all of which are rational. The product of rational expressions is still rational, and this proves our claim. This will be a useful shortcut that is relevant later. Once again, the fundamental method by which we will solve all of these hypergeometric identities is by telescoping. If we can write a term f of n in the form s of n plus 1 minus s of n, then when we sum f of n, all of the middle terms will cancel, and the answer is simply s of n plus 1 minus s of 0. However, telescoping isn't just useful for solving sums, it can also be useful for solving products. If we can write f of n in the form s of n plus 1 divided by s of n, then we can multiply all of the f of n terms and see that, once again, the middle terms cancel, leaving us with s of n plus 1 divided by s of 0. So telescoping can be pretty flexible, being applicable with any operation that has an appropriate inverse. But the different ideas that telescoping can enable beyond its direct application are even more powerful and impressive, as you will soon see. The basic general theme you will see throughout these videos is this. Hypergeometric terms are pretty annoying to deal with, but by dividing two of the terms, they cancel to form rational functions, which can then be further reduced to polynomials, which become easy, although tedious, to solve for. So we want to reduce hypergeometric solutions to rational solutions to polynomial solutions. Keep an eye out for how this happens in each of the algorithms. Okay, let's now do a quick summary of what we just learned. Firstly, we will tackle the problem of finding a closed form for a hypergeometric series by converting the sum to a recurrence and then solving for a closed form. A common strategy employed by the algorithms is by reducing hypergeometric solutions to rational solutions to polynomial solutions, primarily by using telescoping. In addition, just like the last video, we will be shortcutting a lot of the straightforward algebra. Alright, let's dive into the algorithms now. Okay, let's now start on the first step, turning a summation into a recurrence. We will introduce what is called Sister Celine's method. We begin by declaring that we are looking for a recurrence of this form. Again, this might look kind of intimidating, with the nested summation, but this is actually really simple. These alpha functions are simply polynomials with variable n, which is what we are trying to solve for. The capital I and j denote the width and height of the term table we made earlier. This double summation is simply saying that there are polynomials of n for each of these terms in the table, such that the sum of this entire table is 0. Note that these polynomials we are solving for are only in terms of n, with no k's involved. Now, I want to clarify some terminology. I know that these alpha functions are polynomials of n, but I will be referring to the polynomials in their entirety as coefficients, even though I just said they were polynomials. In a normal polynomial, we declare a particular variable, and the real numbers multiplied in front are considered the coefficients. Here, we treat the function terms f as if they were the variables, and so the alpha polynomials here would be coefficients relative to them. I will try to be clear what form the coefficients take when I describe them. I just wanted to explicitly point out that just because I use the term coefficient doesn't mean that they are restricted to real numbers. This abstraction will hopefully make understanding the bigger ideas a little bit easier by analogy. So how would we solve such a ridiculous sum then, where we are not only solving for a huge amount of variables, but the variables themselves are polynomials? It's actually, once again, pretty simple, just once again very scary looking. Let's try a simple example. Suppose this is the summation we are trying to find a recurrence for. Notice that we are summing over all integers k, and let's assume that this sum has what is called compact support, meaning that beyond some finite values for k in either direction, the terms all equal 0. The reason we do this is because if we sum f of n k plus I over all integers k positive and negative, it doesn't matter what this I shift index is, the result is always the same total capital F of n. First, assume some positive integers for I and j. We will assume 2 and 2 here. Now lay out a table of the appropriate size. Remember, the sum of all of the terms in this table should add to 0, and the polynomial coefficients a through d are what we are trying to solve for. Now divide the entire equation by f of nk. The right side is obviously still 0, but notice now that by taking a ratio, all of these f fractions are now rational expressions. Let's now write the polynomials a through d as just a single letter for abbreviation, just to make things a bit easier to see. Multiply the entire equation by the common denominator, and now we have a polynomial equation. We have now just demonstrated the general theme I mentioned before. We took cumbersome hypergeometric terms, reduced them to rational expressions, and then to polynomials. Next, we group all of the same powers of k together. Even though the coefficients a through d are polynomials, they are only in terms of n, so they won't affect the degree of k. Now, since this entire left side is equal to 0, we can set all of these coefficients equal to 0. As you can see, we now have 3 independent linear equations with 4 variables, meaning that by setting one variable to be arbitrary, we can solve for the others. Even though the coefficients here are polynomials of n rather than real numbers, this still gives us a solution, because in theory, we could find a plug-and-chug formula to solve these linear systems. The free variables we have, in this case the coefficient a, we can just set that equal to 1. Finally, all we need to do is sum the equation across all values k, and we have our recurrence for our original f function. Note that the free variables we assign values, in this case a, were arbitrarily chosen, but it doesn't matter what you choose, because the end result recurrence will be equivalent. Phew, that was exhausting. Fortunately, what makes this method so ugly is also what makes it so beautiful. This algorithm is completely routine, requiring no human intuition, meaning that you can simply just write a computer program to do all of these steps for you, which is the entire point of this video. However, there are probably still some questions that remain. For starters, how can you guarantee that all hypergeometric sums will have a solution by this method? Suppose your choices for I and j give you no solution. Is there actually no solution, or did you just not pick a large enough I and j? How can you tell? Let's start by proving that all hypergeometric sums will have a solution by this method. In other words, no matter what hypergeometric term f of nk you select, you can always find coefficients alpha such that this summation equals 0 for large enough I and j. This idea is so important that it is called a fundamental theorem for hypergeometric terms and functions. Here is how we are going to tackle the proof. Recall our previous example. Even though we had 4 unknowns for our alpha coefficients, the maximum degree of k was 2, and so we only produced 3 equations. We know from linear algebra that if the number of unknowns equals or exceeds the number of independent equations, then the system will definitely have a solution. We will show that as I and j get bigger and bigger, this is guaranteed to happen. In order to do that, we will need 2 things: the number of unknowns in general and the highest degree of k, which would give us the number of equations in general. To begin the proof, suppose we make a table of our f terms like we have been doing, with I terms going across for k and j terms going across for n. Let's divide out f of nk on both sides of the equation to obtain our rational functions as before. What would the degree of the numerators and denominators of these ratios be? Let's first try to figure out what the degrees of factorials look like. Consider this example for f of n. If we were to take a ratio like this, we get this result. If we change the arguments one at a time, watch what happens. Can you see what is happening? This little constant term is a linear combination of the coefficients of n and k. For example, if we had 2n plus 3k factorial in the numerator like this, then f of n plus 4k plus 5 divided by f of nk would give us a product of everything from 2n plus 3k plus 1 to 2n plus 3k plus 23. And we got the 23 here by doing 2 times 4 plus 3 times 5. Of course, this is just the result of a single factorial. Each factorial you include in the expression would contribute another ai plus bj degree to the total degree of k, since everything is multiplied. However, no matter how many factorials you include, it will always be a sum of these coefficients in front of n and k multiplied by I and j, respectively. In other words, the degree is a linear combination of I and j. Well, don't forget that if there was a polynomial factor in the hypergeometric function, then the degree of the numerator just increases by a constant, so we can just add that on if it's relevant. Now let's answer one of the 2 questions we need. If we were to now multiply out the denominator, what would be the highest degree of k? Notice that the least common denominator is simply the denominator of the ratio in the corner of the table here, and it is also where the degree of the numerator is the largest. From Sister Celine's method, from this point, we multiplied out the denominator on both sides. So to get the total degree of k, we simply add the degree of the numerator here to the degree of the denominator here, and we have the highest degree of k in the entire table. By combining what we just discovered, this can be summarized as c1i plus c2j plus c3, where the c's here are just some particular constants that we can compute from the hypergeometric function. Now to answer the other question we need. How many unknowns are there? This one is much simpler, as we can clearly see that this is just the number of ratios in the table, the number of unknowns, the alpha coefficients, which is just I plus 1 times j plus 1. Notice that because there is an I times j term in the number of unknowns, it will eventually dominate and grow faster than the linear terms that describe the degree of k, guaranteeing that eventually the number of unknowns will exceed the number of equations, and the fundamental theorem is now proved. Okay, now that we know a solution is always possible, how do we select bounds for I and j? It would be nice to know where to stop so that we can guarantee a solution can be found, and preferably with tight bounds, so that we don't waste too much computation. It turns out that through the explanation we just went over, it is not too difficult to derive some upper bounds for I and j, but we will actually leave this part out of the video. For more details, you can consult the source of this video's content, which will be linked in the description. There is actually a reason why I chose to skip this part. Firstly, a solution is guaranteed as long as you keep increasing I and j, so technically, the explanation up to this point can get the job done already, assuming the identity is in fact hypergeometric. This completes the section on Sister Celine's method. We can now derive recurrences from our summations, and so we are done with this overall major step to solving hypergeometric identities. However, it turns out there is another method that does the exact same thing but faster, so we will be saving the detailed bounds analysis for that algorithm instead. At this point you might be asking, then what was the point of learning Sister Celine's method if something better exists? Was my time wasted? Let me reassure you that it wasn't a waste, because the next algorithm actually also requires the fundamental theorem. The point of introducing Sister Celine's method was to motivate why we might care about the fundamental theorem, and now we are simply going to put it to more use. Even better, the techniques and concepts learned from Sister Celine's method will be important to the other algorithms, so we may as well learn them anyways. The next algorithm we will be looking at is a precursor and component to the faster Sister Celine's method. This next algorithm is called Gosper's algorithm. For those who watched the previous video, this will be familiar. This time, we will be going into a bit more detail so that the motivation and intuition will be a little bit more clear. So what is the goal of Gosper's algorithm? In short, take a hypergeometric term t. Gosper's algorithm tries to find a way to express this term t of n as z of n plus 1 minus z of n for some hypergeometric term z. In this way, this makes the summation of t, the goal of this video, much easier as it allows telescoping. Once we have this z term we are looking for, the sum of all the terms t is simply z of n plus 1 minus z of 0. For those who have some familiarity with calculus, this is kind of like trying to find the integral of a function, except instead of summing continuously, we are summing discretely. And so the derivative, analogously, is taking a difference of its successive terms. Right now, it looks like this algorithm will just jump from our hypergeometric sum pretty directly to the final closed form, without needing the recurrence at all. We will address this later. Let's begin by restating that both t and z are hypergeometric terms, and that t of n equals z of n plus 1 minus z of n. The goal is to solve for z, given t. In order to achieve this, we will first try to reduce the solving of the hypergeometric term to the solving of a rational term. If we were to divide z of n by t of n, a simple substitution in some algebra gives us this. Notice that z of n plus 1 divided by z of n is rational by the definition of a hypergeometric term, and so z divided by t is clearly also rational. Let's call this rational function y. Now we can multiply both sides by t to get that z equals y times t. Let's substitute this expression for z into our starting equation here, and we get this. Let's now substitute this ratio here, which is again rational by definition, with r of n. Notice that we are looking for rational solutions of y now, rather than hypergeometric solutions, and clearly, a solution for y would give us a solution z. Now the brilliant part is that this recurrence can be further reduced, so that instead of solving for rational solutions, we can just solve for polynomial solutions. In order to do this, we need to examine this r of n coefficient here. We are now going to write this rational expression in what I will call Gosper canonical form. What is Gosper canonical form? This r of n expression will be split into polynomials a, b, and c, where a and b form a simple ratio, multiplied by c of n plus 1 divided by c of n. There are some additional constraints, but we'll explain those a bit later. Consider this example. We want to rewrite this rational expression r by finding the polynomials a, b, and c. There are lots of ways of doing this. One way is just by setting c of n to be 1, sort of ignoring c entirely. Another way is to move the factors from a and b over to c. Here's how we can do that. Choose a factor of a and a factor of b, where the coefficient here in a is larger than the coefficient here in b. Start by moving these over to c. Unfortunately, this doesn't quite work, because if the bottom was c of n, the top is not c of n plus 1. There is an easy way to fix this. Simply apply telescoping in the reverse by including all of the cancelled factors in between. You can move any pair of factors from a to b in this way, as long as the a coefficient is bigger than the b coefficient. Not only can you pick which pair of factors to move in this way, you can move as many as you like. Clearly, there could be multiple ways to represent a, b, and c. Since we are calling this a canonical form, we need to pick a method by which there is always one unique way to represent this rational expression. The additional constraints to a, b, and c are given here, but I'm going to use a visualization to try and simplify what this is saying. Let's use a visualization to make the conditions easier to understand. Let's use this rational expression as an example. Rather than represent this as an algebraic expression, I will represent it by drawing points on number lines. For the numerator, I'll make a number line where I plot points on them according to the coefficients of each factor. I'll do the same for the denominator. Let's now take a look at what moving factors from a and b to c would look like in this new visualization. First, we just directly copy the numerator to a and the denominator to b. Now select a point in a further to the right than a point in b, as the coefficient in a would be bigger than the coefficient in b. Let's move them over to c. Just as we had to insert the cancelled factors in between, now c has to include these points in the number line. So now we can see that we have several choices for how to move these factors over to c. We could do nothing, we could do this, or we could do this. Let's now see what the three additional constraints are saying relative to this new representation and the moves we are making. This constraint says that there can't be any common points between a and c, which would disallow this, because the reverse telescoping to fill in points crosses over a point we could have used. This means that when we select factors from a and b to move to c, we have to pick the ones that are closest together, to avoid the crossing over. This constraint says that there can't be any common points between b and c of n plus 1, which would mean this would not be allowed, for the same reason as the previous condition, but for the denominator. Similarly, we need to pick the pairs that are closest together. The first constraint simply says that if you translate b of n any amount to the right, including 0 steps, none of the dots can line up, which means there cannot be any points in a further to the right than any points in b, so something like this would not be allowed. Put together, this simply means that when resolving the pairs of factors of a and b to move to c, you have to keep moving the closest possible pairs until you can't move anything else. If you don't move the closest possible pairs, you would violate conditions 2 and 3, as you would be crossing over other a or b points. And you also have to move as much as possible, or else you would violate condition 1. This can be guaranteed by simply starting from the left moving right, and as soon as you find a numerator factor that violates the condition, move it to c by pairing it with the closest factor in the denominator. So for this rational expression, the Gosper canonical form would be written like this. Alright, now that we have the Gosper canonical form of a rational expression, what's the point? What can we do with it? Suppose we do one more substitution, setting y of n to be b of n minus 1 times x of n divided by c of n, where x of n is yet another rational function. When we substitute all of this back into this equation, we can see that many of these factors cancel, and now we can multiply both sides by c of n, leaving us with this equation here. We have turned the problem of solving a recurrence for rational solutions into solving another recurrence for rational solutions. It appears on the surface as if we haven't made any progress, but there is actually a way to prove that x of n here is guaranteed to be a polynomial. We will demonstrate that x of n must be a polynomial by a proof by contradiction. Suppose x of n could really be written as a fully reduced rational expression f of n divided by g of n. Notice that for whatever g of n we write, between g of n and g of n plus 1, we can always find a factor in one but not the other. The lowest factor of g of n can't be in g of n plus 1, and the highest factor in g of n plus 1 can't be in g of n. And so, this highest factor in g of n plus 1 must also be in a of n to cancel out. And the lowest factor in g of n must also be in b of n minus 1 for the same reason. Otherwise, we would have a rational expression on the left side and a polynomial on the right, a contradiction. However, this results in another contradiction. If we shift b of n minus 1 up to b of n, we can see that the lowest factor of g of n plus 1 is in b of n, and the highest factor of g of n plus 1 is in a of n. This violates the constraint of Gosper canonical form that says that all of b of n must be to the right of a of n. Even in the case of the denominator being a single linear factor, we can't avoid this problem, which guarantees that the denominator can't have any linear factors. This means the denominator must be 1, proving x of n is a polynomial. Okay, beautiful. We are now able to turn a problem where we were solving for hypergeometric solutions into one where we solve for rational solutions into one where we solve for polynomial solutions. The last step is to solve the polynomial recurrence using what is called the method of undetermined coefficients. Let's take a look at an explicit example to see what this looks like. Suppose that this is the polynomial recurrence we end up with. We can now solve for our x of n polynomial. For now, let's assume the degree of the polynomial x of n. In this case, let's try 2. Set up a general form, then plug in and solve. You will get a linear system, and once you solve it, it will give you your polynomial x of n, which you can plug back into Gosper's algorithm to get the answer you're looking for, solving the problem. However, there is a small wrinkle to this problem that needs to be addressed. Sometimes you will get no polynomial solutions from your assumed degree. Unlike sister Celine's method, which we know guarantees an answer thanks to the fundamental theorem, it is possible that there is no polynomial solution here at all. Those of you familiar with calculus might remember that some indefinite integrals can't be solved, even though the definite integrals can. Sometimes this happens with the discrete cases too, like with this identity. Even though a definite sum over all of the integers is possible, an indefinite sum over any number of terms is not. In cases like this, Gosper's algorithm does not give us a solution. So now we have a problem. Suppose you didn't find a polynomial solution for your given degree. You could continue to test higher and higher degrees, but how would you know when to stop? How can you tell the difference between a scenario where the degree isn't high enough versus a scenario where there just is no solution? We can first find the maximum possible degree for the solution, which we will denote as d. If we can find this d value, then by simply assuming the polynomial is degree d, we are guaranteed to find a solution if it exists. And if we get no solution still, then we are confident that there's just no solution. Let's now calculate d. Let's start with the polynomial recurrence we want to solve. To start, notice that our goal is to get the two sides of the equation to match, which means the degree of the left side has to be equal to the degree of the right side. Now let's define these two functions here that give us the degree and the leading coefficient of the polynomial, respectively. Here are the degrees of each of these polynomials. We now add these degrees because the polynomials are being multiplied. Let's suppose the leading terms in these two expressions don't cancel. When does that happen? This either happens when the degrees are totally different or the leading coefficients are different. In this case, whichever term gives the higher degree, that's the degree of the entire left side, which must be equal to the degree of the right side. Solving this gives us this expression for d. But what happens if the first term does cancel? This only happens if the degrees of the two expressions are equal and the leading coefficients are equal as well. In that case, the degree of the left side would be reduced by 1 due to the cancellation. And since the degrees of a of n and b of n are equal, we can just write an expression for d like this. However, there's a small problem. This expression only works if the second highest term doesn't cancel. If the second highest term cancels, then the degree would be even lower, and this analysis wouldn't work. Let's additionally define some variables for these two values just for convenience. If we write out the first two terms of each of these polynomials and realize that we don't really care about the terms that come after, we can simply do some dirty algebra and distribution to eventually get the entire left side to be written as this. This term is the second highest degree, and we need to set the coefficient equal to 0 for it to cancel. The c coefficient in front can't be 0, as it is the leading coefficient of our solution x of n. Therefore, this other factor must be 0. Solve for d and you get this expression. Do take a careful note here. I have defined a and b here to be the second highest degree coefficients of a of n and b of n minus 1 respectively. Notice that is the coefficient of b of n minus 1, not b of n. Our degree analysis is now complete. We don't have to check for further terms being cancelled, because we have covered all the possible cases. Keep in mind that the degree analysis we just did here is only valid for first-order linear recurrences. In addition, there is a small nuanced detail we should point out. While these two cases can't ever happen at the same time, as we can clearly see from the beginning which case is relevant, it's possible for a polynomial recurrence to have solutions in both subcases here, as these subcases depend on the solution. In any case, we now have a maximum value of d we can calculate, which gives us a complete solution for our method of undetermined coefficients, and that completes Gosper's algorithm. Let's now take everything we have learned and do one example together by hand, putting everything we learned together. Let's try this problem. Intimidating, isn't it? Let's now start by stating the goal of Gosper's algorithm, to write the hypergeometric term being summed as a difference of successive hypergeometric terms. First, we need to reduce from solving for a hypergeometric solution to solving for a rational solution. Let's calculate the successive term ratio R of n. Expand, then cancel the factors to simplify. We are going to try and solve for a rational y of n in this recurrence, which would allow us to find z of n. Now it's time for the next step, where we reduce the rational to the polynomial. First, we need to write our R of n in Gosper canonical form, because we need a of n, b of n, and c of n for the next step. We begin by just throwing all of the numerator into a of n and all of the denominator into b of n. Now we need to find factors of a of n that are to the right of factors in b of n. And we can see that only this degree 4 polynomial satisfies this condition, so we move it to c of n. Because they're already successive terms, we don't even need to include any telescoping factors to fit it into c of n and c of n plus 1. We now have fulfilled all of the conditions, so we just need to solve the polynomial recurrence now. Let's first figure out the maximum degree of x of n. We can see that a of n and b of n have the same degree, but the leading coefficients of a of n and b of n are not the same, so the leading terms will not cancel. C of n is degree 4, so in order for the degrees to match, x of n must be degree 2. After plugging in and doing some tedious simplification, equating the coefficients, we get our x of n. All we have to do now is plug all of these expressions back into our equation to find our z of n. Fortunately, almost everything cancels, simplifying this computation quite a bit. And now we have our z of n, and our sum is simply the difference z of n plus 1 minus z of 1, thanks to telescoping, and we have our final answer. Isn't it amazing how a rote algorithm was able to solve such an ugly sum? So let's do a quick review of what we learned so far. Sister Celine's method is able to take a hypergeometric summation and turn it into a recurrence where we are looking for hypergeometric solutions. This recurrence is guaranteed to exist thanks to the fundamental theorem. We are still unable to solve the hypergeometric recurrences at this time. Gosper's algorithm is kind of like a discrete integral for hypergeometric terms, able to express a hypergeometric term as a successive difference of some other hypergeometric term if possible. Gosper's algorithm does this by taking a hypergeometric term and turning it into a first-order polynomial recurrence, which we can now solve using the method of undetermined coefficients. But unfortunately, it is limited to only where indefinite sums are possible. Sister Celine's method fully solves the first part of the problem, turning sums into recurrences, as mentioned before. While Gosper's algorithm is able to directly solve hypergeometric sums in some cases, Gosper's algorithm has additional value in being a component of the algorithms to come, as well as being key to the foundation for understanding a faster approach to the step of turning hypergeometric sums into recurrences. The last two algorithms not only make heavy use of Gosper's algorithm, but also extend upon its ideas. However, there is another very cool application to Gosper's algorithm that we will now introduce here, which is the concept of a proof certificate. Whenever a computer comes up with some result, we shouldn't just blindly trust it, because the computer could make mistakes. It is often unlikely that the computer deviates from its normal intended behavior, but it is far more likely that humans implementing some idea have introduced logical errors. And so, it would be nice if there was an independent way to verify the results of these computations. The WZ method provides such a way. As the computer is finding solutions to these identities, it can also produce a proof certificate, which in this case is a rational function. The proof certificate is simply substituted into a proof template, which, if successful, verifies that the proof was valid. Here is how the WZ proof algorithm works. First, state the identity you wish to prove. Then divide the right-hand side from the entire equation. We are now looking to prove that the sum of f of nk is equal to 1, which is equivalent to the original problem. Suppose r of nk is your proof certificate. Multiply that to f to obtain g of nk. F and g now make up what we call a WZ pair. In a future video, we will explain some very interesting relationships between the two functions. The magic step is now testing that this equation is true. The reason why we care about this equation is that if you were to sum both sides of the equation over all integers k, the right side telescopes and just annihilates to 0. The sum f can be moved to the other side of the equation to show that no matter what the value of n is in this sum, the result is always constant. Finally, all you have to do is plug in an arbitrary value for n, such as 0, and show that the result is equal to 1. This proves your identity. Let's try with an example. Suppose we wanted to prove this classic combinatorial sum here using this proof certificate. First, we write out the summation and divide the right side to both sides of the equation. This gives us our f of nk function, which we want to show that if summed adds up to 1. Plug in our proof certificate to find g of nk, then plug both f of nk and g of nk into the next step. Write out all of the binomial coefficients, simplify, and cancel until you can show that both sides of the equation are identical. This tells us that the sum of f of nk is constant. Finally, pick any n value, in this case we will pick n equals 0, and show that the sum of f of nk over all integers is 1, and we are done. This is the power of the WZ proof method. Now that we know how to apply the proof certificates, how would we obtain them? The answer involves using Gosper's algorithm. Let's use our example from before. If we wanted to find a proof certificate for this identity, we can simply set the summand to be our f of nk. We need this equation to hold true, so first we substitute f of nk into the left side of this equation. Now treat the entire left side as a single term, and Gosper's algorithm is exactly what you need to find the g function on the other side. Let's run through this example step by step. First, let's declare what our t of k is. Next, we need to reduce this to rational solutions, and to begin, we need to know what r of k is. I'm going to shortcut the algebra on this one. Next, we want to put our rational function r of k in Gosper canonical form. We bring the numerator to a of k and the denominator to b of k. These two factors here can be moved to C of k, since the coefficient in A of k is ahead of the coefficient in B of k. Do be careful here. We don't need to do any reverse telescoping, since the 2k makes these two factors already adjacent. Check for yourself that C of k and C of k plus 1 are as they should be. We can now plug our a, b, and c functions into our linear recurrence and guarantee that if there are any solutions x of k, they will be polynomials. Let's do our degree analysis. Since the leading terms do not cancel, our maximum degree is the degree of C of k minus the degree of A of k or B of k, whichever is higher. Thus, our maximum degree is 0, which means x of k must be a constant. Solving, we get x of k is equal to minus 1, which allows us to plug this back into our y of k and final output z of k. Notice that since our proof certificate is g of nk divided by f of nk, g of nk is just our z of k output, and f of k is just our t of k input, the ratio z of k divided by t of k, which we define y of k to be, is the rational function that is our proof certificate. So that was a lot to digest, but hopefully this made a lot of the intuition from the previous video clearer. In the next video or two, we will look at the faster algorithm for obtaining recurrences and then solving the recurrences. As usual, for more information and some exercises, please see the source of the video's content in the description. Feel free to leave any comments or questions you might have. Before you go though, I do have a channel announcement. Is there some math topic you would like me to cover and you want to support me financially at the same time? Thanks to the AbleBees platform, you can now do exactly that. On the AbleBees website, you'll be able to start a petition requesting content from me or pitch in to an existing petition. If enough people pitch in, I will accept the petition and the video will be made. There's also no risk to you, as you won't be charged unless I deliver the content. So if there's that one topic you really want me to cover, come start or join a petition. Oh, and please keep it to one video per petition. Otherwise, as usual, thanks for watching. And if you enjoyed my content, please like, subscribe, and share this video, which also helps my channel grow. Hopefully, the next videos in this series won't take me nearly as long to make. See you all next time.